Well, good morning, folks. Today's topic is complex numbers. And before we get started on what they are, which is an extension of the real numbers, I want to talk about why it is that we need them. I want to do so by analogy, first off. Think about negative numbers. Negative numbers don't really exist in the real world. I can have 3 apples or 5 apples or maybe even 0 apples, but what does it mean to hold negative 3 apples? I think the answer is it could represent a debt or it could represent a deficiency of apples. We use negative numbers because we need them to solve problems with positive numbers. For example, maybe the cost of producing X units at your factory is negative 0.1 X squared plus 45X plus 10,000. So the number of units you're going to produce is positive. Let's say we make, I don't know, what are these calculators? Let's say we make 100,000 calculators, and that costs us $400,000. So the input to the problem is a positive number. It's a real number of calculators I can hold, and the output of the problem is a number of dollars, and it's a positive number. It's an actual amount we could have in cash. But I needed this negative number here in order to get from that positive input to that positive output. This term gives us the economies of scale that says as we produce more and more calculators, it gets more efficient. We couldn't really successfully model this problem without this negative number here, even though all the numbers in the problem are positive and the answer to the problem is positive. Now, complex numbers are pretty much the same way. Complex numbers ask, what if I could take the square root of a negative number? And the answer is, well, that's not a real number. That's not a number of things you can have, positive or negative. And so it might seem ridiculous to study them, but the applications are a little beyond us right now. But for example, in fluid dynamics or electrical engineering, there are problems where the parameters are all real numbers, like the description of how the fluid is flowing, the shape of the pipes, or maybe the shape of the nose of your aircraft. Those are all positive numbers. And your output is all going to be positive numbers, the air pressure at each point. But in the middle, we have to have these square roots of negative numbers to get meaningful answers. And the reason for that is that they depend on quadratic equations. So quadratic equations of the form ax squared plus bx plus c equals 0. We've seen these a couple of times now. We looked at factoring to help solve these in Unit 1. And then in the previous lecture from this one, we saw how to use factoring to actually finish solving the problem. These are going to be our topic in section 2.5, is all the different ways to solve these. So again, a little bit of a preview here, but you've probably seen the quadratic formula at some point. It says that if this is true, then x is negative b plus or minus root b squared minus 4ac, all divided by 2a. So this is a formula for the solutions x that make this whole thing equal to 0 in terms of the parameters a, b, and c. And we need all 3 of those to get the value of x, of course. I want to point out in this formula this plus or minus here. What that's doing is saying I could take negative b over 2a and add this radical over 2a, or I could take negative b over 2a and subtract this radical over 2a. And that's going to give me 2 different solutions. For example, if I wrote x squared minus 5x plus 6 equals 0, for example, then I could factor that as x minus 2 times x minus 3, because those add up to negative 5 and multiply to positive 6. And then the zero product property tells us, well, if these 2 things multiply to get 0, they can't, one of them has to be 0. I can't take 2 numbers that aren't 0 and multiply them and somehow get 0. Real numbers don't work that way. I think That's one of those facts that's deceptively simple and almost impossible to prove, but I think if you look at your intuition, you'll see that it's true. Think of two numbers, neither of which is 0, that multiply to get 0. Can't do it. So that means that either x minus 2, that number is 0, or x minus 3, that number is 0. So either x equals 2, add 2 to both sides, or x equals 3, add 3 to both sides. So we're getting two different solutions to most quadratic equations. And this plus or minus tells us we're getting those two solutions. Now, I did the algebra here and an example here, but one of the themes of this class is that algebra or geometry can often tell you the same fact. We get a symmetry there between them. So let me show you geometrically how this looks. I said that if I draw the graph of a quadratic equation, like y equals ax squared plus bx plus c, then that graph is a U-shape that we call a parabola, right? And in this case, if I had y equals x squared minus 5x plus 6, those solutions, when y equals 0, that's here and here. This is the x-axis, and it's all the points where we don't go up or down from the origin at all. These are all the points where y is 0. So the solutions to this equation, the solutions where this whole x squared minus 5x plus 6 equals 0, are this x value and this x value. So this has to be the point 2, 0, and this has to be the point 3, 0. Does that make sense? So that's why we're getting these two solutions, x equals 2 or x equals 3, is because this thing is shaped like a boomerang, and it crosses the axis and then comes back and crosses the axis again, goes back the direction it came from. So that's this parabola. And in this case, we see those two solutions real easy. And quadratic equations show up all over engineering, all over physics. So we have to be able to find the solutions of these, and sometimes those are like the in-between step to solve the problem. We plug those back in and process them some more and end up with the solution to, say, how the air flows around the aircraft wing. Now, the thing is that not every parabola crosses the x-axis twice. Some parabolas are going to cross the x-axis here. And the trick here is that this is the point. Remember, the equation is negative b plus or minus root b squared minus 4ac over 2a. So how can there be only one solution when there's a plus or minus here? Well, the answer is that this whole term is equal to 0 in this case. And so the solution, if that's 0, there's only one solution, and it's negative b over 2a. We'll see that quantity again soon. So this is that one solution. But there's an even more confounding case, and that's where the parabola is up here or down here. Now, I need those two solutions. I need those two solutions to plug into the next step of my problem and find out how the air flows around the aircraft's tail. But they're not on the real number line. And this is where we need complex numbers. The problem here is that this b squared minus 4ac, in this case, it's a negative number. So I'm taking negative b plus or minus the square root of a negative number, and it's not on the graph. You can't take the square root of a negative number and have it be anywhere on the x-axis. The x-axis is just a real number line, 0, 1, 2, 3, -1, -2, -3, and there's no place for the square root of a negative number. So what I need to do to have these intermediate answers is I have to have some way to be able to talk about the square roots of negative numbers that isn't on the number line. And so that's what complex numbers are for. We have to be able to talk about the square root of a negative number. The answer is not going to be a real number. It's going to be a complex number. So it's not going to be a real, but we have to be able to talk about them so that we can get solutions to all of our quadratic equations. Excuse me, so that we can get solutions to all of our quadratic equations and then move forward from there. So here's what we're going to do. We're going to start with a specific negative number, arguably the simplest one. And I'm going to say the square root of -1. I'm going to define that to be equal to I. So this is just, I picked the letter I for imaginary. Imagine that we could take the square root of -1. I like to use this symbol, a colon and then an equal sign. I like to use that to mean I define it to be equal. So I'm not saying I can prove it's equal. I'm saying this is my definition of the letter I here. So that's what I use this symbol for. We'll see that again a few times. So I'm going to say I is defined to be the square root of -1. I got this from some programming language. I think maybe Visual Basic, but I forget now. Python? Might be Python. Okay. Sidetrack aside, I'm saying, let's say that the square root of -1 is equal to I, and so that means that I squared is equal to -1. We can use either of these as the founding definition of the complex numbers. I guess the question is, where is that supposed to live on a number line, and how do we do math with it? Can I make up mathematics that's consistent with this definition? You remember we had our definition of exponents? Back in section 1.2, we defined exponents, and then we saw, okay, for math to be consistent with this new definition, we have to have the product property and the quotient property and the nesting property. So making up one definition, because it was useful to us, got us a whole lot of useful formulas in mathematics that have to be true if that definition is true. And this is kind of the same. I'm saying I need this definition in order to be able to talk about the roots of this parabola. They need to be somewhere that's not on the real number line. So we're going to see a whole lot of consequences of this definition today. Everything we do today is going to come back to this definition, or this one, they're equivalent. I like this one a little more because it doesn't have a radical sign in it, but that's just an aesthetic preference. It's nothing real. Get it? Nothing real because complex numbers aren't real? The pun was not intended, but I like it. We're going to see what are the consequences of imagining that we can take the square root of -1. First thing is, this isn't a positive number. If I take any positive number, like 4 is a positive number, and I square it, I'm going to get a positive number. So positive number squared is positive. I'm abusing notation really badly here, but you see what I mean, right? Positive number squared is positive. And if I take number, it's not going to be negative either, because if I take a negative number, like say -3, and I square that, this is -3 times -3, the minus signs cancel out, and we get a positive number. So anything negative squared is positive. Okay, so that's our first problem. These imaginary numbers, like I, they can't be positive and they can't be negative. So if I draw a number line, all the positive numbers are over here, and all the negative numbers are over here. So this is the number line. I can't be on the right-hand side of this graph because it's not positive, and it can't be on the left-hand side because it's not negative. So we're not going to go left or right on the number line to graph I. We're going to go straight up. We have to put it somewhere, and it's certainly not 0, so I'm going to go straight up and say, this is where I is going to belong. It's something completely different from the real number line. It's not a real number. It's not positive. It's not negative. It's its own thing. It's its own separate direction. So if that's I, then I can go from 0 to I in this direction. What that means is if I take 2 times I, well, look, 1 was to the right, and 2 times 1 was twice as far to the right. -1 was to the left, and 2 times -1 was twice as far to the left. So we can extend our intuition and say 2i has to be twice as far up. And then 3i would have to be up here. So it's like we've got a whole extra line of imaginary numbers. That has to be there. And if that has to be there, if I is going to be consistent with our mathematics, I have to be able to multiply numbers by it. I can't make up a new number and then say, oh, and you're not allowed to multiply by it. That would be ridiculous. So if I multiply by 2 or 3, I end up here. If I multiply by a half, I'd be right where my cursor is right now. If I multiply by -1, I'm going to have to go down here. So now we've got the other side of this line. Here's where -I would have to live, -2i, -3i. If this definition is going to make any sense, it has to look like this, basically. So we call this the real axis. Let me label these. And we call this the imaginary axis. Again, I for imaginary. Okay, so, and the imaginary axis, it exists because I have to be able to multiply things by I if I'm going to be able to do mathematics with it. That's multiplication. Well, I also have to be able to add and subtract to it. So the question is, what am I going to do with a number like, I don't know, what, 3 plus I? What am I going to do with a number like this, 3 plus I? This number could be saying, well, the 3 says we go 1, 2, 3 to the right in the real direction. That the 3 is a real number, it goes here. And then I is an imaginary number, it goes up here. Well, look at it this way. If I say what's, let me use a different color, 1 plus 2, I could say I go 1 to the right, that's a 1, and then I add 2 to the right to that, 2. So I'm going 1 to the right, and then I'm going 2 to the right from there, and I get to 3. So 1 plus 2 is 3. That's how the number line works. This is, well, what is this, like 3rd grade? So this is taking us way back to the number line, but that's how the number line works, is, I can add 1 to the right to 2 to the right, and that tells me, oh, I'm at 3 to the right. So this is going to be the same thing. Let me get rid of these green lines here now. Whoops. Well, we're going to be stuck with that one then, aren't we? Whoops, did it again. Yeah, there we go. That's as good as it's going to be. 3 plus I, what I'm going to do is I'm going to say, okay, just like 1 plus 2 was 1 and then 2, 3 plus I is going to be 3, like so, and then I. So 3 plus I is going to live right here. Now, you should be getting flashbacks to plotting points in the Cartesian plane, because it's exactly the same thing. I went 3 in the real direction and then 1 in the imaginary direction. It's like saying the imaginary axis is how far up or down you go, and the real axis is how far left or right you go. It's like a Cartesian plane. So if I wanted to plot, I don't know, -2 minus 2i, that would live right here. -2 minus 2i. So this isn't a Cartesian plane because it's all about these complex numbers. But what we'll call this is the complex plane. So just like real numbers live on the real number line, complex numbers live on the complex plane. So I just used the fact that I want this definition to work with addition and multiplication means that this thing has to exist, this geometric object of the complex plane that we extended from the real number line. But now I'm going to take that and go back to the algebra from here. So in this class, it's really useful to be able to dodge between algebra and geometry as it suits you. And this is one of those cases. So if this thing has to exist, there is no other way to make this definition work with mathematics, addition and multiplication, than to construct this thing. Now I'm going to learn something from this thing. And that's, if it's just like the Cartesian plane, and it is, well, that means I can talk about any complex number, any number that's a consequence of this. So whether that's the square root of -9 would be like 3i, so that'd be up here, or 3 plus I, or 2 minus 2i. These are all complex numbers. Any number that lives in this plane is a complex number. And so if it lives in this plane, then I have to be able to plot it like a point. I have to be able to say how far left or right we go and how far up or down we go. So what that's telling me is that any complex number, any number that I have to be able to talk about as a consequence of making this definition, it's two-dimensional. It lives on that flat plane. So we have a real part to go left or right, and we have an imaginary part to go up or down. And that's enough to specify a point on the plane. Just like Cartesian coordinates, if I tell you how far left or right and how far up or down, there's only one point I can be talking about. So same thing with complex numbers. So what this gets us is that any complex number can be written with the real part and the imaginary part. I'm going to call the real part A, some real number A. The imaginary part, if it's up or down, it's multiplied by I. It's in the imaginary direction, so we'll call that BI. Whether that's B is 0 or 1 or -3 or 5, that'll be the part that tells us how far up or down we go. So any complex number can be written as A plus BI, where A and B are two real numbers. We call those the real part and the imaginary part. So this is standard form. We're going to be seeing this a lot. This is the standard form for a complex number because it tells you how to plot it on the plane. A tells you how far left or right. BI tells you how far up or down. So 3 plus I, A is 3, B is 1, tells you to go 3 units to the right and 1 unit up. And scrolling. -2 minus 2i, A is -2, B is -2. That tells you to go 2 to the left, -2, and 2 down, this -2. So that's the standard form for a complex number. And by the way, I'm ready to tell you why they're called complex numbers. Something like 3i or -5i is called imaginary because it lives on that imaginary axis. Complex means multiple part. Multiple, plex part. Like a duplex is a house with 2 residential units. Complex means, we should really call them duplex numbers because I can always write them with these 2 parts, the real part and the imaginary part. They're like the 2 houses in a duplex. So that's where the word complex comes from, is it's a number that's made of these 2 parts. And so this is the real part and the imaginary part. So that's the anatomy of a complex number. Did not mean to open that. Okay, here we go. The question is, if I can write every complex number in this form, then what about weird things like 2 minus 3i plus I squared? You can imagine ending up with this form as you're trying to work with complex numbers. What happens if I get an I squared? Well, the trick here is, from my definition, I said I squared equals -1, right? So I can say this is 2 minus 3i plus -1, and then combine these like terms here and say, okay, that's, whoops, I didn't mean to write that. This is the same as 1 minus 3i. So 2 minus 3i plus I squared is really just 1 minus 3i. Anything that I can do with imaginary numbers, so square them or cube them or take them to the 10th power, I should be able to rewrite back down to this form. I should be able to write it in standard form because it's made of real numbers and i's, so it has to live on the complex plane. And that means I have to be able to describe it as how far left or right I go, how far up or down I go. So it shouldn't be a surprise that I can make any complex number into this form with the 2 parts, standard form. So I squared we got from the definition. That was easy enough. That was real good. What do I do with I cubed? There's a dicey problem. What is I cubed supposed? I know I squared is -1, but the definition doesn't tell me I cubed. Here's what I'm going to do. I'm going to use the product property for exponents. If i's are going to work with our mathematics that we've developed so far, they have to be consistent with everything we've done. We have to keep math consistent with this new definition. And if math is consistent, that means all of our exponent properties have to work with i's. So I could say this is I to the power of 2 plus 1, right? 3 is 2 plus 1. And the product property says that's the same as I squared times I to the first power. With me? So I squared is -1, and I to the first power, anything to the first power is itself, so that must be I. So I cubed is -I. So if I had an expression, for example, like this is an example, this is an example. If I had an expression like 3 plus 2i plus I cubed, I can replace I cubed with -1. So that's 3 plus 2i minus, oops, with -I, sorry. Combine like terms, this is 3 plus I. Okay, same logic. I to the fourth is I to the power of 2 plus 2. So it's I squared times I squared by the product property, which is -1 times -1 by our definition up here. I squared is -1 in both cases. And we know that -1 times -1 is 1. So that's a weird fact. We just found out that I cubed is -I. And we found out that I to the fourth is 1. And where we go from here is real fun. That means if I want I to the fifth by the same pattern, that's I to the fourth times I to the first, right? You've seen this twice now. That's my logic, because 5 is 4 plus 1, skipping this step. And I to the fourth is just 1, so that's 1 times I, which is I. So I to the fifth is the same as I. We went in a big circle. And that means I to the sixth is like I to the fourth times I squared. So that's -1. And I to the seventh is -I, and I to the eighth is 1 again. We followed the same pattern. I, -1, -I1. I, -1, -I1. We're following the same pattern over and over. When I say we go in a big circle, I mean that very, very literally. Here's the complex plane again. Here's 1. Here's I. Here's -1. And here's -I. Now look at this pattern. Here's I to the first. Here's I squared is -1. And then here's I cubed is -I, like we just saw. And we just saw I to the fourth is 1. And then we keep going in this circle, because this is also I to the fifth. And this is also I to the sixth. And this is also I to the seventh is I cubed, or -I. And I to the eighth, like I to the fourth, it's 1. So if you need to find any power of I, you can just follow it around this circle. How cool is that, right? For some reason, and it's not just I, for some reason, multiplication in the complex plane goes in a giant circle. That's just how multiplication works out here. I'll show you another example at the end of this lecture, because I think it's one of the most beautiful things about complex numbers. I really do. But first, this means if I asked you on a test, what is I to the 13th power? You could say, follow my cursor here. First power, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I to the 13th is I. Now this is the geometric solution. Also, you could say I to the 13th is equal to I to the power of 4 plus 4 plus 4 plus 1, which is equal to I to the fourth, I to the fourth, I to the fourth, and an I, which is 1 times 1 times 1 times I, which is I. Math is consistent, so you get the same answer whether you do this algebraically or geometrically. So if I gave you a problem like, hey, tell me about I to the 99th power, big power, I don't really want to count around this circle 99 times to find out which of these 4 places I land on, because boy howdy, the chance that my cursor is going to slip and I mess up my count is pretty high. But I could say 99 is 96 plus 3. and 96 is divisible by 4, right? See here, 13 was 12 plus 1, and 12 was divisible by 4. So it was a bunch of 4s and then a 1. Here, it's a bunch of 4s and then a 3. It's I to the 96. That's 24 4s. So that's just 24 1s times I cubed. So the answer is going to be I cubed, which is negative I. So, going even further, if I asked you what's I to the power of 2,607, you would say 2,607 divided by 4 is, oh, why do I do this to myself? 651 remainder 3. And I don't care about the 651. That means there's 651 4s in the number. So I'm going to have 651 1s here times I. So that's 651 1s times I cubed. So my final answer, the remainder is what's important. I to the 2607 is the same as I cubed. So there's our answer. So that's how you can find any power of I. Kind of fun. All right. Up next. Now that we've got that, if I'm going to be able to work with complex numbers, I have to be able to add, subtract, multiply, and divide them. They have to work with our 4 arithmetic operations, or else they're no good. The good news is adding and subtracting is real simple. All you have to do is combine like terms. Honestly, you can pretend that the I is a variable and everything will work out. So if I said, what's 4 plus I plus 3 minus 2I? You would say, well, that's 4 plus 3 is 7, and I minus 2I is negative I. So you could just drop the parentheses and combine like terms. 4 plus 3 is 7, I minus 2I is negative 1i's. Or if I said 5 minus 3I minus negative 2 plus I, well, 5 minus negative 2 is 7, and negative 3 minus 1 is negative 4. So adding and subtracting complex numbers, all you have to do is combine like terms. If you just pretend I is an X, then you already know how to do this. Very simple. Adding and subtracting is no problem. Multiplying is a little bit trickier, but you already know how to do it. We can just FOIL. So if I asked for 2 plus I times 4 plus 3I. Oh, I'm going to go on a tangent about this one. I can feel it. I can feel it coming. Let's get the algebra done first. I can FOIL and say, first, here, let me show 12 extra steps, right? First is 2 times 4. To show you that this is really just the same. Outside is 2 times 3I. Inside is I times 4. And last is I times 3I. These are all added together. So when I FOIL, I get 8 plus 6I plus 4I plus 3I squared, cubed, squared. Now combining like terms could get me 6I plus 4I is 10I, but I want always with complex numbers, the easiest way to write them is in standard form. So I always want to there's no reason to ever not write a complex number in standard form. It's always better to write them in standard form. There's no application where you'd want it in any other form. So give your answer in standard form. That means combining like terms isn't enough. This 3I squared is a problem. That's not standard. Standard is to have a real part and an imaginary part, and that's with I to the first power. There's a spot on my back that itches that I cannot reach. Hold on just a moment. There we go. Got it. That's better. Okay. 3i squared. Thing is, once again, everything comes back to the definition. I squared is -1. So this is the same as 8 plus 6i plus 4i. What's 3 times -1? -3. Now I can combine like terms and say 8 minus 3 is 5, 6i plus 4i is 10i, and that's our final. Okay. And now for the tangent. Oh boy, I'm really excited. Here's how I said multiplication in the complex plane is a giant rotation. And the whole thing is a carousel. And here is what I mean by that. Here is 1, 2 plus I. Here's where 2 plus I lives. And 4 plus 3i. So 1, 2, 3, 4 plus 1, 2, 3. Here's 4 plus 3i. This is not content you will need to know to pass this class. This is too beautiful for me not to show you. Okay, and then 5 plus 10i. Whoa, I'm still in eraser mode. 5 plus 10i. 5 and 10 up. Here's 5 plus 10i. Okay. All right, here's what I mean. 2 plus I. To get there from the origin, I have to go in this direction. I want to think about this angle and this distance. We actually know from the distance formula, this side is 2, this side is 1. So this distance is the square root of 5. It's 2 squared, it's the square root of 2 squared plus 1 squared. And then 4 plus 3i, it's a slightly bigger angle. And the distance is going to be 5. 3 squared plus 4 squared is 5 squared. So this is a distance of root 5, and this is distance of 5. This thing right here, you can check my math. But one thing is the distance is 5 root 5. It's this distance times this distance. So the distance from the origin, when I multiplied these two numbers, the answer is the product of their distances. So distance is preserved by multiplication is what I'm saying. But even cooler is this. Check this out. If I take this red angle and add it to the green angle, the answer is exactly the blue angle. So if this was, say, 20 degrees and this was 30 degrees, then the blue line would be 50 degrees. So in that sense, multiplication in the complex plane is rotation. The consequences of this fact are so profound that there's an entire senior level math class you can take to describe them. It's called complex analysis. It's where you analyze the complex numbers. That's an entire semester-long class on its own. We are not going to get into that any further here, but it would have been I would have felt terrible to show you the complex numbers and not mention this absolutely beautiful geometric fact about them. So let's get back to the lecture then. Here's how we multiply complex numbers. Let's do a couple more examples. If I have, say, 7 plus I times -3 minus, let's do plus 5i. First, I'm going to FOIL. First is -21, 7 times -3. Outside is 7 times 5i. That's just, whoa, can't write. 35i. Inside is I times -3. And last is I times 5i. But I don't really want 5i squared. I want to write that as 5 times -1, which is -5. So this is really -21 plus 35i minus 3i minus 5. And you can see how once you get used to these, you're going to start skipping steps. Our final answer, combined like terms, is -26 plus 32i. That's our final answer. See, standard form. And if you plot these three, you'll see that the angles add up again. That's always true. I love it so much. But Important thing here is, yeah, we could just FOIL. So if I asked what is 8 minus I times 3 plus 2I, really what I can do is say, okay, 8 times 3 is 24, and then we're going to have minus 3I and plus 16I for the inside and outside, so I'll just write plus 13I, and then 8 times 2I, or negative I times 2I. Negative I times 2I is negative 2I squared, so that's the same as positive 2, and then my answer is 26 plus 13I. Huh. It's weird that those are both divisible by 13. I wonder if there's something deep there. I think there is. Let's see, this one. Oh, yeah, okay. Yeah, I see it. See if you can work out from this diagram why these are both divisible by 13, if you're interested in a fun puzzle. But I'm not going to go on another tangent right now. I already went on 2 tangents. Oh, this is really fun. This is good. This is good. If I had a plus bi and I multiplied that by a minus bi, you remember with square roots, I did this difference of squares thing with conjugates, is what I called them. Like 1 plus root 2, the conjugate would be 1 minus 2. This is exactly the same thing. I call these two numbers complex conjugates. And what I get is the first is a squared, outside is negative abi, inside is positive abi, and last is negative b squared I squared. So these cancel. Negative b squared I squared is negative 1. So that's negative b squared times negative 1. Our final answer is just a squared plus b squared. So if I did, say, 4 minus 3i, if I multiply this guy by its conjugate would be 4 plus 3i. My answer is going to be 4 squared plus 3 squared. My answer is going to be 25. Let's check. First, 4 times 4 is 16. Outside, 4 times 3i plus 12i. Inside, negative 3i times 4 is negative 12i. There's the 2 that canceled, just like I said. And last is negative 3 times positive 3 times I. So negative 3, well, geez, I don't need to write 3 squared. Negative 9i. Well, I squared is negative 1. The 12 i's cancel out, so this is just 16 plus 9. Like I said, 25. Listen, folks, I can't resist. Let me graph this problem real quick. Real quick. Here's 4 plus 3i. Here's 4 minus 3i. These angles are equal opposites. So when I multiply them, the angles cancel out, and our answer is out here. This is the positive, this is like positive 37 degrees, and this is negative 37 degrees. So since I said multiplication is rotation, add positive 37 degrees to negative 37 degrees, you're going to get 0 degrees. You're going to be a real number. So I can make a algebraic proof that when you multiply by the complex conjugate, you always get a real number. Or I can make a geometric proof that when you multiply by the complex conjugate, you always get a real number. They're just so pretty. Okay. This gives us a way to divide by complex numbers. Dividing by complex numbers, this is our last task. Let's start simple. If I want to do 1 divided by 4 plus I, you could say, oh, your answer is 1 over 4 plus I. I mean, this is a complex number. It's just the thing is, this is very much not in standard form. So our goal isn't quite just to divide. Our goal is to divide and write our answer in standard form. Like, this is a complex number. I have to be able to divide by complex numbers or the math doesn't work. So I'm assuming that there's an answer. But I know that that answer lives somewhere in the complex plane, so I have to be able to say it's this far to the left or right and this far up or down. So it has to be able to be written as a plus bi. How am I going to do that? If I want to write this good, I want to write this as a plus bi. What I'm going to do is use trick, multiplied by the complex conjugate. So I'm going to multiply the top and bottom by 4 minus I, Since I multiplied the top and the bottom, these cancel out. They don't change the value. But what's going to happen is now the numerator is 1 times 4 minus I. That's 4 minus I. Tell you what, you can try foiling if you want. I'm going to go a little quicker. I'm going to say A is 4, B is 1. 4 squared plus 1 squared is 17. 16 plus 1. You can foil it if you want and see that this is the right answer. The plus 4 and the minus 4i will cancel out. So that's the outside and inside taken care of. First is 4 times 4, that's 16. Last is I times negative I, that's positive 1. So it really is 17, but I like the a squared plus b squared shortcut. It's real quick. All right, one more thing is I do want to write this in standard form. So I'm going to distribute the denominator. I'm going to write this as 4/17 minus 1/17 I. Every once in a while, MyOpenMath gets really, really picky about wanting this form and not that form. That's like the word. That's one thing I don't like about MyOpenMath is it's super picky about complex numbers. So make sure your answers are always in this form for complex numbers, especially in section 5.5. But yeah, there we go. We divided by a complex number. We found our answer. If I multiplied 4 plus I by this thing, my answer would be 1. So it's only a little bit trickier if I want to divide one whole complex. Whoops, almost said a word I wasn't supposed to. One whole complex number by another one, like 3 minus I over 4 plus 2I. What I'm going to do is get this thing out of the denominator by multiplying the top and bottom by its complex conjugate. I need parentheses to remind me to distribute. And I'm not going to change the value of the expression, so I'm going to multiply the top and the bottom by the same thing. This is really a fancy way of multiplying by 1, because 4 minus 2i over 4 minus 2i is just 1. So I've multiplied the top and bottom by 1, but that's going to let me manipulation that turns the denominator into a real number. So now I have a little work to do. In the numerator, I'm foiling. I'm doing 3 minus I times 4 minus 2i. I'm going to FOIL to get the numerator. So first, 3 times 4 is 12. Outside, 3 times negative 2i is negative 6i. Inside, negative I times 4 is minus 4i. And last, negative I times, oh, that's a lot of minus signs. Negative I times negative 2i. Let me write this down on the sidebar here. Negative I times negative 2i is, the minus signs cancel out and we get 2i squared, which is the same as negative 2 because I squared is negative 1. Just didn't want anyone to get lost here. So that's minus 2. I'm using my trick again. 4 squared plus 2 squared, 16. So let me write this down in the sidebar as well. 4 plus 2i, 4 minus 2i. Shortcut method. I don't want to FOIL. 4 squared plus 2 squared. 16 plus 4 is 20. That always works. Okay, we can combine like terms. 12 minus 2 is 10. Negative 6i minus 4i is negative 10i. And I'm just going to put this in standard form. 10 over 20 minus 10 over 20i, and I can simplify a little bit. That's a half minus half of an I. Half of an I, that's gross. Sorry. So there we go. We can divide by complex numbers now. That's all there is to it. Just make sure your answer is in standard form. Is there anything else I want to say? Oh, wow. I skipped like a couple of, I skipped a line in my notes in the very beginning of the lecture. I just want to show how to simplify some dumb stuff. I said root negative 1 equals I. I want to show how to actually use these in a quadratic equation, right? So if I ended up with root negative 25, Nathan, that's not what you wanted to write. Negative 25. You know what that's going to be? Remember the product property for square roots. This is the same as, look, if negative 25 is equal to negative 1 times 25, I'm going to write that in the other order. Sorry. It just looks prettier if I say 25 times negative 1. Then root negative 25 is the same as root 25 times root negative 1. Root 25 is 5. Root negative 1 is I. So root negative 25 is 5i. So go on. What's root negative 36? Pause if you want. That's correct. It is 6i. What is root negative 32? Oh, that's a weird one. What I'm going to do here is factor. So I could make a factor tree if I want. 32 goes 8 and 4. This is all 2s. It's 2s all the way down. So what this tree is telling me is I just count the leaves, not the branches. 32 is the same as 2 times 2 times 2 times 2 times 2. So what I've got here is root 2 times 2 times 2 times 2 times 2 times negative 1. And what we're going to do is pairs of numbers can come on out of the square root, just like last unit. Singletons are stuck lonely underneath. So what I've got here is a pair of 2's comes out, a pair of 2's comes out. So that's this guy and this guy. And then there's a 2 left, and there's a negative 1 left. So our final answer is 4 root 2i. And the I is outside of the square root. Okay. So that's how you do like the square root of negative 32. You can go on and practice if you want. What would the square root of negative 72 be? And I mean, pause here if you want. Your answer should be 6 root 2i. Okay. I can't resist. That's the end of the lecture, but I want to show one more absolutely wild fact. If you were in my pre-calculus class, I would end up showing you exactly how to compute this, but it takes a lot more angles and triangles than we need here. But one kind of number we haven't talked about at all is what the heck do I do if I get a square root of I? This is a complex number, so it has to be able to be written in standard form. Multiplication is rotation, right? So here's I, and here's 1. So going from 1 to I, this is 90 degrees. That's a square angle. And if multiplication is rotation, this thing is supposed to be halfway to multiplying by I. So if this is 1 and this is I, then the square root of I should be right here, right diagonal. It should be 45 degrees up. Now, if you remember from high school something called a 45-45-90 triangle, then that might tell you that we go root 2 over 2 to the right and root 2 over 2 up. So the square root of I should be root 2 over 2 plus root 2 over 2i. Now that feels too good to be true, but I can prove it. If root I equals root 2 over 2 plus root 2 over 2i, then I can square both sides. Then I has to be root 2 over 2 plus root 2 over 2i squared. Well, we know how to square a complex number. So let's check. Let's check that this is true. So root 2 over 2 plus root 2 over 2. Oh man, this is an expression. That's equal to root 2 over 2 plus root 2 over 2i times root 2 over 2 plus root 2 over 2i. It's time to FOIL. And I am going to write this one out, because otherwise what would be the point? First, root 2 over 2 times root 2 over 2. Outside, root 2 over 2 times root 2 over 2i. Inside, root 2 over 2, root 2 over 2i. And last, root 2 over 2i, root 2 over 2i. Had enough yet? I'm going to simplify all four of these at once by saying root 2 over 2 times root 2 over 2. When you're multiplying fractions, remember you can multiply across the top and bottom. So this is root 2 over 2 times 2. It's just 1/2. Root 2, oh, let me not skip that step. Root 2 times root 2 is 2. 2 times 2 is 4. Now it's 1/2, see? So using this on all four terms here, this is 1/2, this is 1/2 I, this is 1/2 I, and this is 1/2 I squared. Because it's 1/2, 1/2, 1/2, 1/2. So this is 1/2, 1/2 times I, 1/2 times I, 1/2 times I times I. Almost there. I squared is -1, so this is really 1/2 plus half of an I plus the other half of the I minus 1/2. So these bad boys cancel out. Half of an I plus half of an I is a whole I. So this thing really is the square root of I, because when I squared it, I got I. So there you go. I know that's pretty dang wild, but I just adore complex numbers. If you're feeling feisty, if you want like a real good challenge problem, see if you can tell me what the cubed root of I is. We can solve for it by basically the same method. You're going to have to look up some trigonometry to do it, but I'll give you a hint. It has to do with the 30, 60, 90 triangle. Anyway, that's far and away enough for today. You don't have to be able to do this to pass this class. By goodness, no. You don't have to be able to do this to get an A in this class. If you can put a complex number in standard form, understand the complex plane, just how to plot points on it. If you can add, subtract, multiply, and divide complex numbers, you are golden. Because that's more than enough for what we're going to use them for. Because remember, I started this lecture by saying what I need is to be able to take the square roots of negative numbers. So, yeah. Add, subtract, multiply, and divide, put in standard form. You're in good shape. All right, I will see you around.